So hello, welcome to practice problems for chapter 23. Just a reminder, there is an exam 1 week from today on October 2nd, today being September 25th. Next week, I plan on going over last semester's exam on the 28th, and on the 30th, I'm going to see what you guys want to do. My plan is to come in and basically log in and be like, so what type of problems do you want me to solve, guys? And kind of treat it as a whatever you want. I was going to say yesterday. I will send out an email after class today, kind of giving a what do we want to do type thing. Note to self, send email. Email. Okay. But let's get into it. This chapter was all about magnetic fields and the effects magnetic fields have on things, and then how to create magnetic fields. So I'm going to jump right in. This first problem says an electron moves with a speed of 1 times 10 to the 7th meters per second. And for part A, it's coming straight out of the page. It's kind of hard to draw three-dimensional, but that's what we're saying. And for part B, it's coming at an angle of 45 degrees between straight out of page and the z-axis. And so this is going to kill me to do. And so I have my setup, and it's saying, well, I want to go out of the page. I'll go out of the screen at you. Hopefully it's reversed. I don't know if it is. But we're saying when it's coming right this way, right along this y-axis. And for part B, it's coming up at an angle like this in between. That movement doesn't show up well. It's coming up at an angle like this between y and z. But out of the page and up. So it says for both of them, there's a 0.5 Tesla magnetic field in the positive x direction. For each one, what is the magnitude of the force on the electron? So if you want to find the magnitude of a force on a charged particle, the force is equal to QVB sine theta. That only gives the magnitude. That does not give the direction. And sorry, I'm going to do something preemptively for a few seconds from now. So what I'm going to do is I'm going to say, okay, that's going to be the charge of an electron. Negative 1.6 times 10 to the negative 19 coulombs. The velocity of the electron, 1 times 10 to the 7th meters per second, times the magnetic field, 0.5 Tesla. Oh, only one. I should add another sig fig though. Times the sine of the angle. But if you look at the angle between V and B, they're 90 degrees apart, right? Because one's straight along one axis, one's straight along another. They're separated by 90 degrees. So it would be the sine of 90. Thing is, the sine of 90 is 1. So I can ignore that. And the force I'm going to get will just be multiplying through, which will be 8.0 times 10 to the negative 13 newtons.
Can you show me that? Can you show that one more time where you got the 90 degrees from?
Yeah, okay, so on this picture, right, this is straight along x, that's straight along y. And so if we have y coming out of the page, they'll go out of the screen for you. But if one's straight along x, one's straight along y, that's 90 degrees apart. X and y have to be 90 degrees apart. I mean, I'm turning this to match that picture, but yeah, one's along x, one's along y.
I see. I get what you're saying now.
Okay. Now we also want to do direction. For direction, and we're going to get my background for a split second. For direction, I'm going to use the right-hand rule. And what the right-hand rule shows is that you put your hands pointing in the direction of V, you curl your fingers towards B, and your thumb shows you F. Now, if I do that, that's written. V is out of the page, so it's straight at me. B was to the right, so I'll curl this in that direction. And F, my thumb would point in the direction of the force. So my thumb is saying it's up. So the force must be up. Except I glossed over something here. When I did this, this was a negative. So really, this should have been negative 2 and I just kind of dropped it because I wanted magnitude, because the charge is negative, the force is in the wrong direction. And since the right-hand rule says up, it must be down because it's a negative charge. Anytime the charge is negative, you have to switch the direction after you get it. And so it's 8 times 10 to the negative 13 newtons down. Okay. Now for part B, we go from a vector straight along x and a vector straight along y, right? And I'm not even going to bother showing my z right now. We go from vectors straight along x to straight along y. Need more hands. To this guy coming out at an angle like that. But when I take this and move it out to an angle like that, it's still 90 degrees apart. I'm basically just taking this and just rotating it. There's still 90 degrees between V and B there. What? It's the difference of this and this. And that's it. And since there's still 90 degrees for part B, the force is still 8 times 10 to the negative 13 newtons. That hasn't changed. The only thing that's going to change is the direction. Because as the V moves 90 degrees, so does the force. Now, instead of saying I put my V's flat, I'm going to be putting my V up at an angle and curling my fingers towards B. And now, where before my right-hand rule said straight up, and then it was negative, so it came down, my right-hand rule is going to say off by 45 degrees, but because of negative, swap. And so it'll be 45 degrees off from the negative z. And that would be the answer. 45 degrees between the positive y and the negative z. Any questions though? I have some issues with this problem. I was talking about before I started with Paul that this axis as labeled doesn't work in a Cartesian sense, but we'll get into that later on.
So part B is just interpreting direction, basically.
Yep, because the magnitude will be the same because it's still 90 degrees. Let's go to the next one. This next one says, a uniform 2.5 Tesla magnetic fields points to the right. A 3-meter long wire carrying 15 amps is placed at an angle of 30 degrees to the field, as shown in the figure. What's the force? Well, now I want the force on a wire. I did not think that was red. And the force on a wire is ILB sine theta. Side note, you might notice I always do like a cursive L. The reason for that isn't anything too fancy. The reason you always use a cursive L here and not just an L is because when you're writing it, if you do a capital I, then a lowercase l, and then you start solving for things, shit can get confusing. And so you'll notice I always kind of make a fancy, go all the way out with my I and do the L like that. It really is just to not run into a capital I and a lowercase l looking the same. If you don't do that, it's fine. Just if you don't do that, keep track of the difference between a capital I and a lowercase l. But that's why it's always cursive looking on here. Anyways, if I want to find this force, these are really straightforward problems. The force is just going to be the current times the, I have a mild mistake in the answer. I have the unit for amps being, or unit for length being amps, times the length, times the magnetic field, times the sine of the angle. And it will give me an answer. And that's really all there is to it. Now, if I want direction, because I didn't open up my right-hand rules ahead of time, if I want my direction, it's the same idea for the right-hand rule. I point my fingers in the direction of I, which is up at an angle, and I curl my fingers towards B, but B is straight to the right. So I have to take my hand so I can point straight to the right. And my thumb points out of the page. Wait, is I that way? I, B.
I got a point in the back of myself.
Sorry, that's into the page. I'm pointing my thumb into the page, but looking at the video of myself that's pointing at me, which confuses me. So if I go I, curl the finger towards B, this is pointing at my screen. That's pointing into the page. So the force is into the page. Sorry, I know I said out of the page. It's because I'm literally watching a video of myself pointing at me, which is amusingly confusing me, which is a dumb way to confuse myself. I can't handle mules. But there you go. I is this way, curl the fingers towards B, into the page.
Yeah, I keep using my left hand and it screws me up.
Don't use a left hand.
Dr. Lars, quick question.
Yep.
Oh, and never mind. I see. I thought you dropped amps somewhere, but now I could see it in the solution. Never mind.
The 15 amps.
Yeah.
Yep. To be fair, in the actual type solution, it has 15 amps and 3 amps because I put the units for I put the meters as amps. I will fix that afterwards. That yeah. Okay, these were both really simple. Most simple than anything I put on an exam. Let's go to the next one, which I think is a little more complicated, but really still not much. Normally for the exam, or normally I've only done this once before. For the exam, what I did was I mixed all these things kind of in a weird way. You can see last semester or last year's exam if you go online, but I'll kind of try to show you kind of what I'm doing with it. So what this one says is there's a 200-turn rectangular coil having dimensions of 3 centimeters by 5 centimeters. Is placed in a uniform magnetic field of 0.9 Tesla. Find the current in the coil if the maximum torque exerted on it by the magnetic field is 0.15 Newton meter. Okay. The torque acting on a loop of wire is NIAB sine theta. Well, in this case, theta is a different angle. Theta isn't the angle between I and B. It's actually the angle between, well, no, it is still the angle between. It's the angle between the normal of the thing and the magnetic field. That if this was, I don't have a loop. If this was my loop, it's about 200 turns too. It's the angle between this coming straight out and the magnetic field. And so as it spins, that angle is going to be changing. The maximum value is going to happen whenever the sine theta is 1. And so the maximum torque will be NIAB. Now I want to find I, so I'm going to divide both sides by NAB. And so it'll be the maximum torque, 0.15 Newton meters, over the number of turns times the area. But I didn't give the area, I gave both dimensions. But that's okay. If I want to get the area, I'll just multiply the 2 dimensions together. The magnetic field. Part B says find the magnitude of the torque when you're at 25 degrees. So for part B, I'll just go back to this equation. And I'll just plug in 25 degrees. Now, to be fair, this NIAB, I could plug in now, but I just found out that NIAB was torque max. So I would probably just say torque max sine theta, or 0.15 Newton meter sine of 25 to get 0.063 Newton meters. I could have plugged in for N and I and A and B again. I'm just lazy. Any questions?
So just one more time. So like the logic behind it was that that's the 25 degrees would be the angle, the difference between like the perfect north of the object and
Sure.
its like rotational axis.
It's called the normal normally, but yes, the perfect north, and it would be the angle between that. Oh, you mean north of the magnet? Yes. Oh, so if this is the magnetic field, it would be the angle. Use my shirt as a background. It's more white. It would be the angle is the angle between the magnetic field and the normal of the loop. And so right now, if they'll put it up at 0 degrees, and then as this spins, it'll be changing. Okay, let's try to get something a little more complicated. And this one isn't still that much more complicated. I should really change the packet problems for this chapter to have more to them. But honestly, it's a pretty straightforward chapter, other than the right-hand rule stuff. Did we just lose me? That's not good. Am I still here?
You are now.
Okay, I don't know when I
Yeah.
got lost. My computer showed us connecting to the internet.
You were complaining that this was an easy problem.
Okay. Yeah, basically. So these problems are not that complicated, other than the right-hand rule. On the exam, as I said, I'll probably just have a few parts to make up for it, as you can see last semester's. So this guy says we got two wires, one going on Y, one going on X. What's the magnetic field at point P? So first off, if the direction of the magnetic field is going to follow yet another right-hand rule. Wow, that is really blowy. Where the direction of a magnetic field is you point your thumb in the direction of the current, and the magnetic field wraps around in the direction of your hand. If I do that, I can say the magnetic field is going to wrap around, looking at the one going up, the 6 amp current, it's going to wrap around like so. And so at, just drawing. So for this first guy, the magnetic field wrapping around is going to be into the page on this side and out of the page on this side, wrapping around. Now the guy along the x-axis, if I turn my hands, is also going to wrap around following the right-hand rule. And so this guy is going to be into the page on this side and out of the page here. And so if I look at point P, they're in opposite directions. The one along the y-axis is into the page. The one along the x-axis is out of the page. Now I'm going to find out of the page as positive. It doesn't really matter which way I define positive, because in the end I don't ask for it. Like I don't ask for positive x or positive z or negative z. We haven't really got into that in this class ever. But I'm just saying, I can just say I just pick a direction, make it positive. The other one's negative. But as I said, I'm going to make out of the page negative. The magnetic field from each wire will be mu naught I over 2 pi r. So the magnetic field total will be mu naught I, and I said I'm going to make out of the page positive. The current that's along the x-axis over 2 pi, that distance from the x-axis one, minus mu naught I, the one on the y-axis, over 2 pi times that y-axis one. Now mu naught and 2 pi is in every term, so I'm just going to factor them out. Why am I using such a crappy pen? And plugging in some numbers, I have 4 pi times 10 to the negative 7 Tesla meters over 2 pi times Ix is 7 amps. And the distance from there to the point is 3 meters minus the other one, 6 amps, which the distance from that wire to the point is 4 meters. I just simplified this to do the math. The piece in the parentheses, I'm going to ignore the front for a second, is 7 amps over 2 meters minus 3 amps over 2 meters. Just reducing that. 7 minus 3 is full, which is 2 amps per meter. And so it's going to be 4 pi times 10 to negative 7 Tesla meter times over 2 pi times 2 amps per meter. Not even looking at my solutions. Wait, why am I off by? I'm not getting the same thing my solutions have. Where did I make a mistake? X, 7. I made a big mistake. Somehow this was a 3. Like the distances between, that's a 3. I'm sorry. I don't know how that 3 magically became a 2. Sorry about that. That is not going to reduce nice and neat. That's a bitch. I kind of like it when it reduce nice and neat. So since it doesn't reduce as neatly, I actually have to do the math. It ends up being 1.66 times 10 to negative 7 Tesla. And my units were wrong up here. This is Tesla meter per amp. Dear God, there were so many mistakes on this page. I suck. I gotta redo this entire packet. Sorry about that. I don't know why I read a 2 and read a 3 and made it a 2. Any questions despite my failure?
Why did you take the difference?
Because they're in different directions. So if you
So if
look
they
at,
were in the same direction, we would
then I'd
have
add them. Yep. But since
okay.
the magnetic field is out of the page from the x-axis and into the page from the y, they're pointing in opposite ways. They have to cancel each other. Magnetic field is a vector.
Gotcha.
Okay. Now I can actually even use that same logic on this last one because I'm going to bother doing the last one today. This last one has loops. And it says, okay, I have 2 coplanar and coeccentric circular loops, each with their own current, going in opposite directions. Given the radius of both, what's the magnitude and direction of the electric field, or the magnetic field at the center of the loop? I messed up the units again. Still here, this should be Tesla meter per amp. I will need to go and fix that. Now at this point, it's a single loop. If it was a solenoid, I'd use the solenoid equation, which is written up here. But I didn't give a solenoid here. I gave a singular loop. And the singular loop equation is that the magnetic field really of a single loop is mu naught I over 2R. Now I do still have the issues of direction. And the right-hand rule for this one, I could do the same as the last guy and just say if I put my thumb, my fingers curl in. But you can also do, if you curl your fingers in the direction of I, your thumb gives B. It works either way. In fact, let me open up the last one again. Fine, don't open that up. I could use either one of these right-hand rules, the one we just did, or this new one. I'd probably stick to using the one we just did. I normally do, just so I don't have to memorize so many. And if I go around, I can say, okay, I1, culling. Okay, I1 is into the page. And so I1 or B1 is into the page. B2, curling my hands around, is out of the page. So I'm going to have to subtract them again because they're once again in opposite directions. And so the B net is going to be, which one? Let's have B2. Let's have out of the page be positive. That's the standard. B2 minus B1. Or mu naught I2 over 2 R2 minus mu naught I1 over 2 R1. I'll once again factor out my mu naught and 2's.
Why did we drop the pi?
That's the equation for a loop of while. When I talked about this in class, I kind of said there's a lot of calculus involved. Don't worry about it. Because one while is mu naught I over 2 pi R. But if you have a loop of while, means you have a magnetic field from this piece plus this piece plus this piece plus this piece plus this piece, and the pi's end up canceling out. It's a lot of calc. Does that answer your question?
Yes.
I2, I need those values. I2 was 3 amps. Yep, 3 amps. And O2 was 9 centimeters. The other guy was 5 amps and was at 12 centimeters. Oops, this is Tesla meter per amp. That M's up top. And I can do that math. And when I do that math, I get a negative 5.24 times 10 to the negative 6 Tesla. So I got a negative answer. Let's talk about what that means. See, I said out of the page was positive, and I got a negative answer. So all that means is it's 5.24 times 10 to the negative 6 Tesla into the page. Because I got the opposite sign of what I assumed was positive. What's the last bit? Let all one remain fixed at 12 centimeters. Determine the value of O2 since the net field of the center of the loop is 0. Okay. For part B, this was the magnetic field, this equation here. If it's 0, I can ignore my mu naught I. For it to be 0, that means I2 over R2 minus I1 over R1 is 0. So I1 over R1 equals I2 over R2. Which R are we solving for? Solving for R2. Oh, I'll multiply both sides by R2. Divide both sides by I1. And multiply both sides by R1. And I'm not going to bother plugging in. You guys can see where the numbers come from. That's the general idea. I mean, most of these, the trick is the right-hand rule, but it's a very plug and chug chapter. You don't have anything crazy like the Kirchhoff loops. It's just, hey, what direction are these things in? And you use one of the equations up here. With the exception is this one didn't, this guy did not admittedly have this equation because normally I'd go straight to that one. Take that as you will. Any questions?
Yeah, just a quick question. I think it's an algebra thing, but back in part A, where you did mu naught over 2, I2 over R2 minus I1 over R1,
Hmm.
why did you flip it, not do I1 over R1 minus I2? Like, why did you have 1 or 2 minus 1 typically?
And not
Versus,
1 minus 2.
yeah, that's,
It's arbitrary. I could have done 1 minus 2. So traditionally the positive axis is out of the page, and I know that, so I said the one that was out of the page was positive. But if you went the other way and made into the page positive, it would have been fine. You would have gotten a positive answer at the end and said, I said positive was into the page, I got positive, set. You can make it go either way. But as I said, I normally make out of the page positive. But it'd be fine if you went the opposite direction. You'd still would have gotten the same answer into the page.
okay.
So you
I
know
was
you
just
got that right if your answer comes out positive.
Yeah, because I asked for magnitude and direction. So if you said into the page was positive, you wouldn't have had this negative sign. You would have just gotten 5.24 times 10 negative 6. But either way, the answer is 5.24 times 10 negative 6. The answer isn't negative 5.24 times negative 6. It's 5.26 times 10 to the negative 6 into page. So if you went the other way, you would have gotten a positive, meaning into the page. The way I went, I got a negative, which means into the page. You can go either way. Stoke in here today. Any other questions? Right. I'll fix the few mistakes that were in here, and then repost it. But other than that, I'll stop there. Have a good day.